Okay, so today we're going to take a look at chapter 3 in the text. And this is all about probability. Okay. And so we start off just by saying, if we have some event, okay, we have some event, A, okay, we say that the probability of event A is probability of A, okay? Sometimes can also be written without the R, okay? P of A, probability of A. And I'm a little bit sloppy, and so sometimes I use PR and sometimes I just use P. But I would say they appear both quite commonly in the literature. So however you do it, it's fine. Okay, and this is basically a value that we assign to talk about the likelihood or the chance that an event will that event A will happen. Okay. The likelihood or chance A happens, okay? And so for any event A, the probability of A is always between 0 and 1. Okay, inclusive. Okay, so, probability of A equal to 0 means A never happens. And if the probability is 1, that means A always happens. Or A is certain. Okay. And and I think we're familiar with this concept of probability. We can say, if I flip a coin, the probability that it will land on heads and we would say what? Yeah, 1/2. We would say probability of heads is 0.5 or 1/2. Okay. So far, so good? All right. In this class, we take a classical view of probability, and so we take the frequentist. So we will use the classical view of probability, which is the frequentist view, or the frequentist interpretation of probability. Okay, the other view of probability that is probably more common in some of this later research would be the, versus the Bayesian or Bayesian view of probability. Okay, so we are not doing the Bayesian view of probability, and that's okay. So the frequentist interpretation of probability. So when I say, so I don't know if we've ever thought about this, but when we say the probability that a coin flip will land on heads is 0.5, what exactly does that mean? Does anyone care to volunteer an answer? Okay, go ahead.
50% of the time, when you flip the coin, it will land as heads.
Okay, so I would say this is a good start, but the truth is if I flip the coin 4 times, I'm not guaranteed to get 2 heads and 2 tails either, right? But that doesn't mean the probability isn't 0.5. It is 0.5. It's just it's like that. So
there are 2 options, so it could be one of the 2.
Okay.
Therefore, it's 50% that it can be one or the other.
Okay. Well, and that works only because we're assuming that both sides are equally likely. Okay. Whereas, will my phone ring in the next 10 minutes? There are only 2 options, yes or no. But the answer of no is much more likely than yes, okay? So.
Should we look at it in terms of how big the sample is, in terms of like 100 different throws?
Yeah, okay, so yeah, we're getting at this idea, and so when we talk about the frequentist interpretation of probability, we kind of see this word frequent in there, and so when we talk about, the probability of an event, is the long-run relative frequency, okay? And when we say long run, we're talking approaching infinity, okay? The long run okay, and so, long run, this kind of means so, after, 5, we'll say 10 flips, I could have 6 heads, and so, my current relative frequency would be 0.6, okay? And after 1,000 flips, maybe 506 heads, okay, and so my relative frequency would be 0.506. And what we're just saying is that, after many, many, many flips, okay, the relative frequency would be our probability. And so, the frequentist interpretation, it works for things like coin flips. It works for a lot of things. When we have situations that are not really repeatable, okay, then we might run into some problems of interpretation that might, force us to think of things as funny. So, if we say, after some, let's say somebody gets an illness, and we'll say, the doctor might say the probability of survival after 5 years is 20% or something like that. It's not like we can repeat this experiment or something. Okay, it's not like a coin flip. So with the frequentist interpretation, we have to pretend like we can look at infinite parallel universes, and at this moment in time, if we were to continue look into the future 5 years, in about 20% of these parallel universes, there would be survival, and in the other 80% there would not be. It's a little bit strange, but that's what we have to do with the frequentist interpretation there. Okay, so it's based on the idea of, in the long run, or if we could duplicate this thing many times, what is the relative frequency that we would observe? Okay. Yes.
Does that make it wrong when you say that that's because, if you were to say that's actually because, I'm not saying it is, but that's what you would say, that's actually because 1 in 5 patients actually survive after 5 years, more like the one that is.
So, to say, because every patient is different, right? So,
But isn't that what you're basing off of the actual probability when you say something like patients?
Maybe. I don't know how they're coming up with these numbers, and so it could be, but it could also be, when we or if we just say, so maybe patience isn't a good example, but if we say, there is a 40% chance that the Earth's temperature will rise 2 degrees over the next 10 years or something like that. Okay, we don't have multiple Earths against which to test this thing. Okay, so a statement like that is a difficult thing to test under the frequentist interpretation. That's all. Okay. But for our purposes, this is perfectly fine. Okay. So after many flips, the relative frequency would be our probability, and so this kind of maybe we can make a distinction between empirical probability and theoretical probability. Okay, probability. Okay, so the empirical probability can just be another term for the relative frequency of the event based on actual experimental trials or evidence. Okay. Okay. So after 1,000 flips, our empirical probability would be 0.506. Okay, so after 1,000 flips and 506 heads, our empirical probability is equal to 0.506. Okay. On the other hand, we have the theoretic probabilities. Okay, and this is probabilities based on mathematical rules. Okay, and so what we would say is, the coin has 2 sides, they're equally likely, so the probability of heads is equal to 1 over 2, or 0.5. So theoretic probability that the coin lands heads is 0.5, whereas our empirical probability, which would be based on actual coin flips or actual observations, could be something different, like 0.506. And so we have the law of large numbers, which states that as we increase the number of trials or repetitions, okay, we expect our empirical probability to approach the theoretic probability. Okay. And so a lot of what we will do in the rest of today's course, or not today's course, today's lecture, is learning about the rules for the theoretic probabilities. Okay, so today's lecture focus on the rules and rules of calculating theoretic probabilities. Okay, but empirical probabilities are still very useful. Okay, and they are often used and they are often used to answer questions where the math to get a theoretic probability would be too complicated. Okay. Often used where so, if you had never seen a coin before, okay, and you don't know how coins work, and you say, okay, well, I want to know how often this coin is going to land heads, okay, and you don't have the mathematical ability to say, oh, okay, well, there's one side and there's two sides, 1/2 is 1/2. You could, if you had no idea how a coin worked, you could flip it 1,000 times, you see it land 506 times, and you'd say, okay, well, based on this, I anticipate that in the future, the coin would land heads with probability of about 0.506, okay? And that statement wouldn't be too far off from the truth, and that's just based on your 1,000 observations, okay? So, if there are, there are complicated systems, and this is especially the case, for things like sports, okay? So if you follow sports and you go to any kind of some kind of website, they might talk about, the probability that this team will win, okay? And it'll be like, we predict this team will win with, probability 0.64 or something like that, okay? How are they getting this number, okay? There's no, you can't, as far as I know, there's no mathematical equation that says, okay, we're going to plug in the heights of the players and the weights of the players, and somehow we know exactly the skill level of the players, and we can do all of this, and we're going to get some number. There's no formula for that. However, people have developed simulations. Okay, they can have a computer play a game of basketball against itself, or a game of football against itself, or something, and they can have the computer run through thousands and thousands of these simulations, and if in these simulations Team A wins 64% of the time, then they'll publish and say, we predict Team A will win with probability 0.64. Okay, so it's based on thousands of simulations. These are not based on mathematical rules or formulas, but rather simulations, and it comes down to the quality of the simulation itself. You have a question?
Aren't those simulations actually based on mathematical rules and formulas?
Yes, so there are, of course, there's going to be mathematical rules and formulas underlying the simulation, yes, but there is no mathematical formula that says you plug in these things and you're going to get this probability number, if that makes sense. Okay, so for example, we could simulate a coin flip by having the computer draw from heads and tails with equal probability and see what happens. Okay, but that doesn't require us to say 1 divided by 2 is 0.5. Okay, and so there's no formula that says plug in this team and this team and it spits out a number. In certain cases, you have formulas like that available. Okay, and we'll talk about those rules. But in other cases, we don't have formulas or axioms that get us to that probability itself. We have to kind of get an idea of it through simulation. Okay, and that number, that 64% simulation or result, could be different if on another day we ran another 10,000 simulations. I might not get 64% exactly on another day. Okay, so that 64% is not a precise result of mathematical rules. Okay, yes, there's math, of course, involved in setting up the simulation, but beyond that, who knows, right? So okay, so some empirical rules, these are still very useful. Just I would say that's beyond the scope of this course. If you take a statistical computing class, it'll probably get into stuff like that. Okay, so let's talk about some of the things we can do with probability. Some of our rules for calculating theoretic probabilities here. Okay, so we have just a few basic rules. Okay, so we would say, so we'll say we have event A has probability of A, okay? And this is equal to some number, all right? So we could say, okay, so we could say probability of A equals 0.3. Do not write A equals 0.3. Okay, this is not correct because A is an event. A is not a value. It's only correct to say that the probability of A is equal to some value. Okay, so we would say the complement of A is the event where A does not happen. Okay, So, so we can write the complement of A can be written as not A, or A complement, or some textbooks write A prime, okay? And the probability of not A is equal to 1 minus the probability of A. Okay? And so this, you know, just from simple algebra, this implies, or this comes from the fact that probability of A plus the probability of not A is equal to 1. Okay, so these two things combined cover all possible scenarios. Either A happens or A does not happen, and that covers every possible outcome. Okay. Okay, we have some OR rules for quote OR situations. So if we have events A and B and B, then we would say the probability that A or B happens is equal to the probability of event A plus the probability of event B minus any overlap to probability of A and B. Okay, and this can be illustrated. We often like to draw little Venn diagrams here for this. So here's a circle representing A. Here's a circle representing B. Okay, this part here would be A and B. Okay, so the A or B would represent this shape. Okay, and this is equal to A plus B, but minus, if I do this, I have too much, I have to subtract off the overlap. This is A and B. Okay. So that's the probability of A or B. We have a special case. Okay, and this is A and B are mutually exclusive. Okay. Mutually exclusive means that if A happens, then B cannot happen, and vice versa. So mutually exclusive basically means if one event happens, it makes the other event possible. Okay, so for example, you know, A could be a die roll is the number 4, and B could be a die roll is odd number. Okay, so if A happens, if you get the number 4, then B is impossible. If B happens, if you get the die roll as an odd number, then A is impossible. Okay, so these two events are mutually exclusive, and if that's the case, then the probability of A or B just becomes the probability of A plus the probability of B. Okay, and that's because what is the probability of A and B if they are mutually exclusive? This is 0, right? If they're mutually exclusive, probability of A and B is 0, so it just simplifies to this. I'll kind of section this off too. Are there any questions? Yes?
I was wondering, could you give sort of a like real life example for that first part where
Sure.
they're not mutually exclusive?
Yeah, we can do this. Okay, so we'll do an example. Let's say I have a little table here, and okay, so we'll say we have left-handed and right-handed, and we got glasses and no glasses. So we'll just say these are people, and that might be left-handed or right-handed, and maybe they wear glasses or they don't wear glasses, okay? And I don't know, I'm just making up numbers here. Let's say there's 10 left-handed people with glasses and 15 left-handed people without glasses for a total of 25. And let's say there are 65 right-handed people with glasses, and we'll say 80 right-handed people without glasses. I don't know, what is this? 145 and 95, so this becomes 170. Did I add that right? Okay, so, all right. What is the probability that someone wears glasses? If we pick someone at random, so we're going to be, if I pick someone at random from here, what is the probability that the person I select has glasses? And you would say 75 divided by 170, right? Okay. What is the probability if I pick someone at random? What's the probability that this person is left-handed? 25 divided by 170, right? Okay. So I can ask the question, what's the probability that someone has glasses or is left-handed? Okay. Now, there are a couple approaches to this question, okay? I have all the internal data of the table, so we can one way is to say, okay, left-handed or glasses. Let's just go through each of these things. Okay, do these 10 people count for left-handed or glasses?
No.
Yes, right? So the or here is this is an and or, okay? So anytime you see or in statistics, is always and or.
Sorry, by count, I thought you meant, I thought that would be the square where that's the probability of them being, of probability of A and B, and then you would subtract it at the end.
Okay. Well, so we I understand what you're saying. Okay. So here, probability of glasses or left-handed. It's always an and or. I mean, so in English we don't have this word. We only have or, which could be exclusive or and or, and we have to kind of work around it by saying and or, right? Because I could say, do you like vanilla or chocolate ice cream? And your answer would be yes or no, right? Do you like vanilla or chocolate ice cream? You'd say that. I could say the exact same words, but just with a little change in intonation, and then it changes the question, right? And I'd say, like, do you like vanilla or chocolate ice cream? And then you would say, oh, I like vanilla ice cream, or I like chocolate ice cream, right? So it's, yeah, whatever. Okay, so so anyway, in statistics, whenever you see or, it's an and or. It's not an exclusive or. It's the do you like vanilla or chocolate ice cream? Yeah. Okay. So anyway, You guys get my picture here. So with here, you know, do these 10 people with glasses count? Yes, they do. The right-handed people with glasses, do they also count towards this value? Yes. And the left-handed people without glasses, do they count? Yes, they do. Okay? But then the only people that don't count would be the right-handed people without glasses. And so one way to get this would be to add these up. We would say 10 over 170 plus 65 over 170 plus 15 over 170. Okay, and if we did this, we would get 80, 90 over 170. Okay. All right, and then the other way would be probability of glasses or left-handed. We would say, oh, well, this is our rule of probability of glasses plus the probability of left-handed minus probability of glasses and left-handed. Okay. So the probability of glasses would be 75 over 170 plus the probability of left-handed would be 25 over 170. Okay. And then I would subtract off what? 10 over 170. Okay. And if I do this, I would also get 90 over 170. Okay. And we can see by, you know, by using this number 75, what I'm effectively doing is I'm adding in these two numbers, right? This number 75 represents these two numbers here. And this number 25 represents these two numbers here. But what I've done by adding, if I add 75 plus 25, I've effectively double counted this, and that's why I'm subtracting it out, okay? But I only subtract it out once, okay? You don't have to take them, you don't have to subtract off 10 out of 170 twice or anything like that, okay? Does this, is this okay with everybody, or is there any confusion here? That helps. You're good. Okay. Okay, and so, you know, depending on the scenario, you know, you may or may not have the full table for you to work with. Okay, I could just summarize and say, here's a little quiz for you. Okay, so we'll say the probability that someone likes okay, so we'll say owns a dog or dogs is I'm making up numbers here. Okay, we'll say 0.4, and then we'll say probability owns a cat 0.35, and then we'll say probability owns both cat and dog will be 0.18. I don't know. I mean, I'm making this up. Yes?
Do you omit the 0 before the decimal? Is that a...
No, it doesn't matter. Sometimes it's you know, and I'm a little sloppy on this. Sometimes I put the 0 there, and sometimes I don't.
Thank you.
It's all the same to me. Okay. Yeah. I don't know. Okay. Yeah, it doesn't matter. Okay. All right. So here, let's see if you can answer these questions. What is the probability that someone has a cat or a dog? Okay, So that'll be our first one, and then I'll ask a few other questions. What is the probability that someone has neither cat nor dog? And then we'll say, what is the probability someone has a dog and no cat? Okay, so I'm gonna I'll give you guys like a couple minutes to work this out, and I'll pause the video if you're watching on YouTube. Pause the video here so you can figure out these answers yourself. Okay, so you can either own a dog or not own a dog, right? Those are the only two options that exist in the world. All right, either you have a dog or you don't. There's no. Is there a third option? I don't think so, right? You're either owner of a dog or you're not an owner of a dog. Maybe a dog comes by your house, or like your friend has a dog that maybe your significant other has a dog, but you're not the owner, right? I don't know, or you are. Okay, so and then the same applies for cat and no cat. So either you have a cat or you don't have a cat. Okay, and then so we said owns a dog. That probability is 0.4, right? Okay, so that means no dog would be 0.6, right? Because those are the only two possibilities in the world. They have to add to 1, okay? Cat over here is 0.35, and no cat would then be 0.65, okay? Is this okay with everybody? Okay. All right, and then we have one number here, 0.18. 0.18 goes right here, right? This owns both a cat and a dog, goes right there, okay? And so as soon as I put this number in, the other three numbers are revealed to us, right? Because we know everything has to add up. So if I have 0.18 here, I must have 0.22 here, okay? And if I have 0.18 here, I must have 0.17 in order for this column to add up, okay? And if I've got 0.17 here, this has to be 0.43. Okay, so everything adds up. Okay. All right, and then so now that we have this answers all of our questions, right? Okay, so what is the probability that someone has a cat or a dog? Okay, well, we can do 0.4. So we can say, well, maybe I'll write this out. This could be the probability of cat or dog is going to be the probability of cat plus the probability of dog minus the probability of cat and dog, right? This is just, here I'm just using the rule of probability of A or B is A, probability of A plus the probability of B minus the probability of A and B. Okay, so I have 0.35 plus 0.4 probability of a dog minus 0.18. And what do I get? I get 0.57, I think. Or no. Yes. Okay. Okay, and then what is the probability that someone has neither cat nor a dog? Okay? So we can, I don't know, can figure this out. So there's a few ways, okay? We can look at our table and say, oh, no cat, no dog, that's going to be 0.43. Okay, 0.43 from our table. That's probably the easiest way. Well, assuming you've set up a table. If you didn't set up a table, then you can, then you'd have to think through your logic rules, and you'd say, okay, no cat and no dog is equal to 1 minus the probability of cat or dog. Okay, but this is, I didn't expect you guys to have to figure this out, but but it will give you the same as this. I would say just make the table and go for it this way. Yes?
I think another way where I figured since it's neither of them,
Okay.
and you know, we know that we have 0.4 that have a dog,
Uh-huh.
right? And so if they didn't have a dog, then it would be, the probability would be 0.6, right?
Okay.
And then you take 0.6 and add it to 0.65 because you had 0.35 with a cat, right?
Okay.
And then you subtract 0.82. I was basically doing the same formula, only, you know, the cat or dog, the probability of cat or dog, you'd do the probability of cat plus probability of dog minus the probability
So you're doing
of cat and dog.
0.6 plus 0.65, but how are you getting, you're subtracting off?
The 0.82 comes from the 0.18 that we already had cat and dog.
Oh, okay.
And then I just subtracted that, and it came out to 0.43.
Let me just think. That plus that. Okay, yeah, that'll do it. That'll do it. Yes. Also allowed. Yeah, that would be probability of no cat. Probability of no cat plus probability of no dog minus the probability of no cat or dog.
Well, it was like taking the probability of yes cat, right?
Right.
And then I guess it's basically 1 minus.
Yeah, I think.
That number, right.
Right. You're doing this minus minus the other thing. Okay. Yeah. That works. That works too.
It's really, I think,
Yeah.
more complicated than it needs to be. So I'll go with the other one.
Right.
Thank you.
Okay, and then what is the probability if someone has a dog and no cat? Then we just go, okay, dog, no cat, 0.22, right? I'm just looking at the table. Dog and no cat, 0.22 from the table. Okay. Is that good with everybody? Kinda? Okay. All right.
Did we calculate the owns both cat and dog, or did you just, was that a given?
This was given. These values, these here were given to you. Okay, these were given, and I just made them up. Okay. Yes.
Just so I just assumed like a population of 100 individuals or something just to get rid of decimals and.
Yeah, that's fine.
Or I can do that. Okay.
Yeah, as long as you then divide by 100
Yeah,
at the
turn
end,
it into
right?
percent.
Yeah. Yeah.
So wait, you said again how you found out that, why don't you just take it from the table?
So I think that the table makes everything easier. So here I said, you know, the probability of owning a dog is 0.4. So we started with the edges of the table first. I said if, you know, probability of having a dog is 0.4, then not having a dog must be 0.6 because it has to add up to 1. Same thing with cat and no cat. They have to add up to 1. Okay. And then I put in the spot where people have a cat and a dog, 0.18. Okay. And because we know the rows have to add up and the columns have to add up, the other values in the table are determined here at, you know, 0.22 and all of this stuff. So once I have all of these values, then all of these other answers, I think, become clear. What is the probability that someone has a dog and no cat? I can just look at the table and say, okay, we're going to be in the row for dog, and we're going to be in the row for no cat, and that's going to be, or column for no cat, and that's going to be 0.22 here. Does that help, or is that... okay, yes?
On a quiz, if we have something like this for the last question, can we put from the table the way that did? Do you want it?
Yeah.
Okay.
I mean, if you make a table somewhere on your thing, then I'll know that you've
Okay.
gotten your answers that way, okay? Yeah.
Yeah, I mean, in terms of showing work, you need more character.
Yeah, I mean, you know. Yes.
And for the last question, is there a way of calculating it without a table?
Yeah, you'd just have to think of the intersection here. You'd have to do you'd say, okay, well, probability of dog, this is going to be equal to you know, dog owners with cat and dog owners plus dog with no cat, right? So this is how you could do it without. Okay, so because you say, you know, all dog owners, either you can split all dog owners into two parts, those with cats and those without cats. There's no third option for dog owners. You either have dog owners that have cats, dog owners that don't have cats, right? And then so we know that the dog owners is 0.4, and we know that the dog owners with cats is going to be 0.18, which means the other number has to be 0.22. Okay, yeah.
I just wanted to say it might be useful to think about it in terms of, it's the same thing. You're basically doing the same thing.
Yeah.
In both cases. It's just one of them. It's like writing out properly.
Yeah, so yeah, here I'm doing it this way, and then here I'm just doing it with the table. I think the table takes off the, I don't know, for some people like this way, okay? Dog owners with cat and dog owners without a cat, and they can see it that way. The table does the same thing, right? Dog owners with cat, 0.18, dog owners without a cat, 0.22, so you're right, it's the same thing, okay? Okay, so far so good? All right, we have the and rules, okay? So in the previous example, I said dog owners that have a cat, so dog and cat, I just made up a number, okay? In some scenarios, we have to figure these numbers out ourselves, okay? And so we will say the probability of A and B, you know, is always going to be equal to the probability of A times the probability of B given A. Okay, so this is read as the probability of B given A. Okay, so this just means, this is another way of saying is that if A happens, what is the probability of B? Okay, so that is the probability of B given A. If A has happened, okay, if we know A has happened, what is the probability of B? Okay, and then so when you multiply these two together, you get the probability of A and B. All right, so let's let me explain this with an example here. Okay? Yeah, question.
Does order matter when it's presented like that?
Is there an or? Or
Order.
which order?
Like this probably A and B that it has to be A then B, or is
Oh, no. Okay, so all right. So all right, that's a good. Okay, so probability of A and B is the same thing as the probability of B and A. Okay, those two are identical. All right. I could, because these two are identical, I could also just flip the letters around, and another probability of A and B is also equal to the probability of B times the probability of A given B. Okay, so these two things are identical. Okay. All right, and so this would be the probability of A given B. Okay, but you know, so this is true, but beware. Probability of B given A is not equal to probability of A given B. Okay, these two are very different. Don't mix up B given A and A given B. Okay, so I think all of this stuff will make a little bit more sense with an example. All right. Okay, and so the example that I'm going to use will also introduce this concept of a probability tree. Okay, and okay, so I'm going to just explain some silly scenario here. All right, so let's say you know, we are flying to Chicago or whatever. It doesn't matter. Okay. All right, so if there is a storm, okay, the probability that your flight is delayed, probability of a delay, we will say is 0.6. Okay, so if there's a storm, 60% chance that there's a delay. Okay, and so I can write this as the probability of a delay given a storm. Okay? So keep in mind, you know, I'm not writing probability storm vertical bar delay. It's delay given storm. It's if the storm happens, what's the probability of a delay? That's what we're saying here. If there's a storm, the probability of a delay is 0.6. Okay? All right, so, and then on the other hand, if there is no storm, okay, then the probability of a delay is 7%. Okay? So how would I write this symbolically? So I would say probability of what? Vertical, so it would be delay, vertical bar, no storm. Okay, good. 0.07. Okay. All right. So then, and then, you know, you check the weather. And then it says, okay, the probability of a storm is 25% or 0.25. Okay, so this will just be probability of a storm is 0.25. Is that okay? All right, so then I'm going to ask you a question. I'm going to say, you know, first question will be, what is the probability that there is a storm and you get delayed? Okay, so first the storm has to happen, and then on top of that, you have to have the bad luck to be delayed, right? So what's the probability that's going to happen? So this would be probability of storm and delay, and we would say this would be the probability. So just following kind of the equations of the A and the B and the whatever, this would be probability of storm, and I would multiply this by probability of what? Delay given storm. Is this okay? All right, and so this is going to be 0.25 times 0.6. And you multiply that out and you get 0.15. So far so good? Okay, so because here I'm just replacing A and B with storm and delay and things like that. Okay, so let's, we're going to try this same stuff with a probability tree, okay? And I'm going to just take our, the key pieces of information I have. So I have probability of delay given storm is 0.6. I have probability of a delay given no storm. What did I say? 0.07? Okay, and then I said probability of a storm, 0.25. Okay, so we're going to draw a probability tree. Okay, so we'll draw a tree. And we're going to say, okay, well, tomorrow, one of two things can happen. There's a storm, or there's no storm. Okay, that's it. I probably should have said inclement weather or whatever. Okay. All right, so the probability I walk down the storm path is 0.25, which means the probability of no storm must be 0.75. Good. Okay. All right, and then if there is a storm, one of two things can happen. Either I end up delayed, or even despite the storm, the airline has it together and there's no delay. Okay. All right, so what's the probability that I get delayed over here? 0.6, okay. And then what's the probability of no delay? 0.4, right? Okay. So this you know, what is this symbolically, this 0.4?
No delay given storm.
Yeah, so this is, you know, I'm not going to write this for all of these, but this would be probability of no delay given storm. Okay. So, you know, that's kind of an interesting thing, that the complement of delay given storm is no delay given storm. Okay? And those two things have to add up to 1. Okay, and then if there's no storm, I can still be delayed for other reasons, okay? Or there's no delay. Okay, so what number goes up here? 0.07. And what number goes down here? 0.93. Okay, and so we can go down all of these things, and we would get all of our the and things. So everything here, these are all given probabilities, but when I multiply this times this, I get the and probability. So I could do 0.25 times 0.6, and I get 0.15. And this is going to be the probability of a storm and a delay. Okay. And then when I multiply these, I get 0.10. And I don't know what these numbers are. 0.75 times 0.07. 0.0525, and so this must be 0.6975, I think. Okay. All right. Is that okay? All right, so then I could ask other questions, like where can I write these questions? I've run out of space here. All right, I'm going to just copy this and paste it onto the next slide. Make it a little bit smaller and stick it in the corner here. Is that still semi-legible for you guys? Okay, so I'm going to ask you questions like, regardless of the weather, what is the probability I get delayed? Okay, and so what would you answer me there? 0.2025, exactly. Okay, and so the answer here is there are two ways to be delayed. Okay, this would be probability of delay and storm plus the probability of a delay and no storm. Okay, and I can just add those two together, the 0.15 and the 0.0525, and I don't have to worry about any overlap because those are mutually exclusive. I cannot have been delayed and experienced a storm and at the same time been delayed and experienced no storm. Okay? So yeah, this is just 0.15 plus 0.0525 to get that number. Is that okay? All right, let's try another question here. Okay, so I'll say, so let's say you're the friend picking you up from Chicago. Okay, so now you're in Chicago, you're waiting on your friend. The screen says flight's been delayed. Okay, and so you go, oh, I wonder if there was a storm. All right. This is my contrived scenario here. Okay, so you say, okay, so the flight has been delayed. Okay, what is the probability that there was a storm? So to answer this, we would have to answer, okay, so well, symbolically, what is this? The flight has been delayed. What is the probability that there's a storm? This would be what? Probability of a storm given delay. Okay, so symbolically, this is probability of a storm given a delay. And I haven't answered how, given you a formula for this, but this is the thing that we're going for, okay? So once we know that there's a delay, this reduces our world of scenarios down to just two possibilities, okay? So this is no longer a possible scenario, and this is no longer a possible scenario, okay? Because now that it's been delayed, I cannot be in this no delay scenario, okay? So I've reduced my world just down to these two possible scenarios here, okay? And of these, one of these happens because there's no storm, and then the other happens when there is a storm, okay? And so what we're going to do is we're going to take this 0.15, which is the probability of a storm and a delay, and we have now reduced our world just down to these two scenarios, which is effectively just the world where there is delays. Does that make sense? Yes? No? Kind of?
Just go over that again.
Huh? Yeah.
You could just review it.
Yeah. So now that it says the flight has been delayed, we have reduced. So there used to be 4 possible scenarios, right? When we woke up in the morning, there were 4 things that could happen today, right? There could be a storm, there might not be a storm. There could be a delay, there might not be a delay, okay? So, I could experience storms and delays, storms and no delays, no storms and delays, and no storms and no delays, okay? So there were 4 possible scenarios when we started, okay? But now I've told you the flight has been delayed, okay? And that eliminates the scenarios now where there was no delay. We are now reduced to just these 2 possible scenarios, okay? And so, and what I want to know is, well, what was the probability that I was in the scenario with the storm? Okay, and so there's one scenario, the one where I'm delayed and I experience the storm, and then there's the one where I'm delayed but I don't experience the storm. Okay, and so I'm going to take the probability of the storm and the delay, and I'm going to divide it by basically these 2 added together. which is the probability of the delay. So I'm going to have 0.15 divided by basically 0.15 plus 0.0525. Okay, so I'm going to do 0.15 divided by 0.2025, and we would say 0.741. So what was the probability that there was a storm? Basically about a 74% chance that there was a storm, if we know that the flight's been delayed. You know, assuming all of these numbers are correct. Is that okay? Okay there? Okay, so then, so what we say here is that the probability of A given B is equal to the probability of A and B divided by the probability of B, okay? Or, you know, flipping it around, if you have probability of B given A, this is the probability of A and B divided by the probability of A, okay? And this is actually, if you just look at the algebra, this is just a circular definition, because earlier we said the probability of A and B was equal to the probability of B times the probability of A given B, right? Okay, or, you know, and this would be equal to the probability of A times the probability of B given A. Okay, so we can see how all of these things, they just relate to one another. Okay, and so you know, depending on the information provided to you, perhaps you know, you're given this piece and you have to figure out this piece, or perhaps you're not given that and you have to figure out the other pieces of information. So you just kind of have to read through the problem. So right, so you know, here if I multiply both sides by the probability of B, I would end up with the probability of A and B, and this would be the probability of B times the probability of A given B. Okay, so this is just algebraic, from algebraic manipulation. Okay, should I give you another example problem for you guys to work through? Yes, let's do that. Okay. All right, so we'll say the probability that a random patient has a certain disease is, we'll say, 1 in 1,000. Okay. There is a test for the disease, okay? Okay, so we will say the test reports positive with probability 0.99 if the patient has the disease. And then, but the test also reports false positives as a false positive rate of, we'll say, 2%. So this basically means test says positive for disease-free patients 2% of the time. Okay. All right, so then the ultimate question is, if a patient gets a positive test result, what is the probability this patient actually has the disease? Okay. All right, so I'll give you guys a few minutes to work through this. And if you're watching on YouTube, you can pause the video here so you can try it out yourself. Okay, so we'll go over the answer here. And so I'm going to just flip to the next slide here, and I'm going to start by kind of labeling the things I have. So I'm going to just start off and I'm going to say the probability of disease is 0.001. Okay. And then one of the sentences said, okay, if you have the disease, then the probability of getting positive given the disease, this is 0.99. And then the other one said, if you don't have the disease, you can still get positive, so this is probability of positive given no disease is 0.02, okay? So I hope everybody's okay with this part so far, okay? So, you know, I often like to kind of turn the statements that I see in the problem into kind of these, you know, slightly, you know, more symbolic notation here, just because when dealing with the, I don't know, the numbers and stuff, I think this kind of serves as a guide point here. Okay, and then there's always the question, well, do I make my tree start off going positive and negative, or disease, no disease? Okay, so you have to, you can't do the plus, positive, or negative if the only information you have is based on a given thing. Okay, if you had positive or negative by itself, you could do it, but we don't have that. We only have probability of positive given a certain part. So you have to do that that part first, okay? Because that's going to decide what's given and what's not given. So we're going to draw our branches into disease versus no disease. And we're going to go down the disease side with probability 0.001, which means this side has probability 0.999. Okay? And then we draw the split into plus or minus. Okay, and then so given the disease, or if we have the disease, if the patient has the disease, the probability of a plus result is 0.99, and that means the probability of a minus result will be 0.01. Okay, and then over here, if there's no disease, the probability of a positive result is 0.02, and the probability of a negative result will be 0.98 then. Okay, so far so good? Okay, all right, and then so now we can kind of multiply things down the line, and if I were to do that, I would have, you know, 0.001 times 0.99, and I would get 0.00099. And what is this? This is probability of disease and positive. Okay. All right. But the question that we were asking was, if someone gets a positive test result, right? If a patient has a positive test result, what is the probability the patient has the disease? Okay, so the question here is, what is the probability of disease given positive? Okay? And so, you know, a common mistake, or just a common things that students struggle with, is just getting disease given positive mixed up with positive given disease. Okay? And so just make sure you can keep those things straight. Okay? And so, you know, if we kind of compare this to the symbols, you know, probability of A given B versus, you know, whatever, this is going to be the probability of disease and positive divided by this part over here, probability of positive. Okay? All right, so we have disease and positive. That's going to be 0.001 times 0.99, or this 0.00099. Okay, so we have the numerator. Okay, and so now what is the denominator? Okay, so the denominator consists of just the two scenarios. Now that we've said the patient has a positive result, we've really limited ourselves just to you know, this scenario and this scenario. Okay, we've eliminated the situations where patients can have negative test results. Okay, and so here, you know, I have this one calculated, and then over here I need to calculate this 0.99 times 0.02. 999 times 0.02 gives me 0.01998. Okay, and so the probability of positive is going to be a combination of 0.00099 plus 0.01998. Okay, so these are disease and positive plus no disease and positive. Okay, and I add those two together to get the total probability of being positive. So I would do this plus 0.00099. Okay, and so I have 0.02097 on the bottom. Okay. So is this okay with everybody? All right. Okay, and then so I just do that multiplication, or I mean just do that division. 0.00099 divided by this number, 0.02097, and I get 0.04721. Okay, and so this is if you think about this result, this is actually maybe a little bit surprising, right? So the test, if you have the disease, it flags positive 99% of the time, okay? And so sometimes people think that, and then they say, oh my gosh, I got a positive test result. Does this mean I have the disease? Well, the probability that the patient actually has the disease, despite the positive test result, is still less than 5%, okay? It's much higher than just a person right off the street. What's the probability that someone right off the street has the disease? That's only 1%. I mean, 1 in 1,000. And here now it's about 5%, but it's still a relatively small probability. All this is basically saying is just basically if you get a positive test result, you're more likely to be a false positive than an actual person with the disease, okay? Because the disease is so rare. And the false positives, it's you know, in comparison to the actual frequency of the disease, it's higher, okay? Okay, why don't we take a short break here, and then we'll come back and we'll talk more about probability stuff here.